All right, everybody, welcome to the week 2 theory video. We have a lot to get to, so I'm kind of just going to fly right into it. We want to define a few new words, a few new adjectives, and kind of just open up our noun bucket or open up our definitions, learn about a few new types of limits, and we are going to also prove a few things today. It's going to be a fun day. We're going to have to know our trigonometry, things like that, and we're going to prove one of my favorite things in a first semester calculus class. Okay, so one-sided limits and limits involving infinity. The limit of f of x as x approaches a from the left. This little negative sign right here means from the left. Okay, so the limit of f of x as x approaches a from the left is equal to L if and only if, remember that's a biconditional, that means that if this is true, then this is true. And if this is true, then this is true. If and only if, for each epsilon bigger than 0, there is some delta bigger than 0 such that f of x minus L, the distance between f and L, is less than epsilon whenever a minus delta is less than x is less than a. So first of all, notice that I am not allowing x to step on a. Nothing changes there. The big thing that changes is the only x values I'm observing are on the left side. That's why this is well named, the left-handed limit. That's what this is called. On the left side of a. Whereas the typical definition, if you recall, I can add it here. This part says something like this: 0 is less than x minus a, which is less than delta. That simply says the distance from x to a is less than delta, but this x could certainly be on either side of a in this case. With this condition, we are only allowing x to be on the left side of a. I've kind of drawn a picture over here. Oops. Notice here's our a, and here's our limit here, of course. Here's our a value. Here's epsilon away from L on the right side, on the top side, epsilon away from L on the bottom side. Notice that the delta bubble, so this point right here would be a minus delta. We only observe the x values in this little interval. In the typical definition of a limit, you would also have the delta neighborhood on both sides, and you'd be able to observe x values and where f of x is on either side of the limit. But in this case, we're only concerned about this left-handed little delta neighborhood, and that's why we have this notation, this right here. We only care about the left side of a, and we go delta away from a. So notice that the picture checks out with our typical understanding of a limit. We can choose this delta so that if we only observe x values within a distance of delta away from a, but on the left side on the left side of a, i.e. x less than a, then all of the function values observed in this interval will be within this yellow band, okay? So that is true in this picture right here. And notice I like what I wrote here. We do not care at all about x bigger than a if we are talking about a left-handed limit. I don't care what goes on the right side. I'm sorry, I might have said left side a second ago. On the right side of a, if we were talking about a left-handed limit. In fact, I could have drawn it probably would have been more fruitful to show that. Notice that on this side, perhaps the right-handed limit does not, or the delta that we chose does not work for the right-handed limit. So I'll keep that there. But anyways, okay, so that's a left-handed limit. That's something we have to at least be aware of, so I spent some time defining it. And of course, that begs the question, there is certainly such thing as a right-handed limit. The limit of f of x as x approaches a from the right, so that means we're going from the right, right? So from the right, we're approaching a from the right. And just like over in the other situation, it was from the left. It sometimes gets confusing thinking about what that means. But this means from the right. This is called a right-handed limit. if and only if for each epsilon bigger than 0, there is some delta bigger than 0 such that the distance between f of x and L is less than epsilon whenever x or a is less than x, which is less than a plus delta. In other words, we are only observing the x values in this little interval on the right side of a. And notice up here, we have grappled the function value. And of course, we do not care about this guy right here. We don't care about f of a or if it even exists. We only care about evaluating the x values on the right side of a within this delta interval. And if we can always find this delta interval, no matter what the epsilon is, if we could always find a delta interval on the right side of a that grapples the function within the yellow bands, then we can say that the limit of f of x as x approaches a from the right exists and is equal to L in this case. All right. So we needed to define those because one of the big results today uses a right-handed limit. So stay tuned for what that means. And also, you should be able to notice that pretty much the original definition of a limit is really just a combination of these two. Indeed, I think I can say that if this is true and this is true, and these numbers L are the same, then the limit itself exists. So in other words, if f of x is approaching 7 from the left, and it's also approaching 7 from the right, then I think I can say in general that the limit of f of x as x approaches a is 7. Okay, and that is a result. You should prove that. It should be intuitively true, but it should be proven. We're not going to spend time proving it. I might give it to you guys as an extra credit or something. Who knows? But we haven't talked about this monster concept called infinity. So we need to define yet another set of types of limits, and these involve infinity. Okay, so let's talk about what these are. All right, this says the limit of f of x as x approaches infinity, or you can say as x increases without bound, is L if and only if for each epsilon bigger than 0, there is some real number n, so that's what this says, real number n, such that the distance between f of x and L is less than epsilon whenever we push the x values to be bigger than, that should say n. Let me fix that real quick. Whenever x is bigger than n. Okay. So let me go over that again. The limit of f of x as x increases without bound is L if and only if for each epsilon bigger than 0, there is some big number n in the real numbers. We want to imagine this as a very big number. We're going very, very far down the x-axis, such that the distance between f of x and L is less than epsilon whenever x is bigger than that big number. So we're pushing x really, really far down the x-axis in the positive direction. So here's what that means, what all that nonsense gibberish means, is if my function acts all insane on the left side of n, I don't care. So I have a limit here, and I go away from the limit by some small number, epsilon. If at some point, as we are walking down the x-axis, if there is some cutoff point where no matter what epsilon you give me, the function is bounded between this epsilon strip for all x values past this big number n, then we can say that the limit of f of x as x increases without bound is equal to L. Okay, so you should always have kind of the entire dialogue of the epsilon delta dialogue. Well, there's no delta in this case. The entire epsilon dialogue in your brain. We can shrink this epsilon. There can't be anything special about epsilon. If at some point, maybe the next number n is much further, if all x values past n forces f of x to be within that epsilon strip, then you can say that the limit of f of x as x approaches, here, let me put the whole thing in the frame, as x approaches infinity is equal to L. And that has to be no matter what epsilon we're talking about. So if I shrink this smaller and I shrink this to make this higher, if I can find some big N such that all x values pass that big N, I observe that my function is grappled within these epsilon strips for all x's past the N, then I can say that the limit of f of x as x increases without bound is equal to L. Okay, so, and we're going to see a few examples, a few famous examples of something like this. And I think I only have one more fancy definition. Okay, yeah, this one's weird. All right, here we go. The limit of f of x as x approaches a is equal to infinity, or f of x increases without bound as x approaches a, if and only if for each real number n, or m in this case, for each real number m, notice this is the first time we're not seeing for each epsilon, so something weird is going on in this case. So for each real number m, and we want to imagine this m as very big, but it is a real number, so it's not infinity. It's a very big real number. Google, or Google to the power of Google, or something insane. There is some very small delta, bigger than 0, such that f of x will always be observed to be bigger than m if we grab x to be closer than delta away from a. Okay, so let's look at the picture. Let me have kind of both in the frame. Here's like a picture of a function that seems to be behaving in such a way. Imagine this m as a very large number. Imagine this delta as very small. We have a here, and notice that if we force delta to be closer and closer to a, then these f values are going to be larger and larger. And if, no matter how big this m is, so like we can push this even further, like I'll do it. We can push that m even larger, maybe right here. Oh, I used that color already. Maybe right here. So here's a new m star. Can we still choose a delta that forces all function values to be bigger than m? And I think we can. Let's see, here we go. So it looks like if I kind of use this far away from delta, I'll call this delta star. Or excuse me, this far away from a, maybe this one. So this would be like, this right here would be a minus delta star, because that delta is associated with m star. And here we go, this other one. A plus delta star. Notice that all these function values rest above the yellow line. Okay? And if that will occur for every single large number m, in other words, if I bring this m higher, then I can just force this delta to be smaller and only observe these tiny little x values that are barely away from a. But if I can always grab that delta, if that delta always exists no matter what m is handed, then we can say that by definition, f of x increases without bound as x approaches a. Or in other words, the limit of f of x as x approaches a, the limit of f of x as x approaches a is equal to infinity. This is a little bit of a cringy notation, because so far we're used to this object being a real number, this limit existing, quote unquote. Some people would say the limit does exist in this case. Some people would say, no, the limit does not exist in this case. I honestly think the limit does not exist in this case, because when I hear the limit exists, that to me implicitly means the limit exists as a real number. In fact, factoid here, infinity is not a real number. So what is infinity? I don't know. I don't care. There's many different ways to interpret what infinity is. It's more like a concept or an idea than any sort of finite or graspable thing. But in particular, the only thing we care about is certainly not a real number. Because if it were a real number, it would have to follow the field axioms. And infinity does not behave like the field axioms. For instance, if infinity was a real number, then infinity minus infinity would necessarily have to be 0. But it's not always 0. So we know that infinity is not a real number. So in other words, we would say that the limit does not exist in this case, but it is equal to infinity. And we're going to have to be able to learn how to deal with this infinity beast, whatever it is, in this class. But this is really important. All of these definitions are really important. But I wanted to look at a specific example, a familiar example that we should all recognize, know, and love. And from this, I wanted to mention a few famous limits that we have to know off the dome quite easily. By observation here, I think that the limit as x approaches infinity of this f of x, which is, of course, the same thing as the limit as x approaches infinity of 1 over x, is equal to, well, I don't know. As I run towards infinity, as our x values run towards infinity, what's going to happen with the height of this function? Well, I think it's going to collapse to 0. If I allow x to be 1 billion, in other words, if I went all the way to 1 billion, this number would be 1 over 1 billion, which is very small. But we haven't reached our goal yet. We never will. So we would have to go past 1 billion. And we haven't reached, or we would have to go past 1 billion, and then this would collapse even smaller. So this gets smaller and smaller and smaller and smaller and smaller, but it is also always positive. So the limit, so here's the thing. This keeps getting smaller and smaller, never stops getting smaller. It's also always positive. If x is bigger than 0. If x is bigger than 0, then 1 over x is bigger than 0. That's something I can prove. So it's always positive, always getting smaller, and any larger number than 0, we can find an x value such that 1 over x is smaller than that x value. For instance, let me say this quickly. I'm spending too much time. If I give you a very small x number, or very small number right here, I can choose x to plug into this guy right here to make 1 over x even smaller, for instance, 1,000,000 or something like that. All this is to say that this limit is equal to 0. This is something that we just have to know instinctively. So the limit of 1 over x as x approaches infinity is equal to 0. That indeed should be proven. If I have time in this week's bonus video, maybe I'll prove that, but hopefully it's at least intuitively true. I also wanted to observe, what would this limit be? Here, let me erase. I think if I erase something as I film, then the video will be as if I never even wrote it, so I shouldn't erase that often. The limit as x approaches 0 from the right of 1 over x is equal to, let's see what this would be. Looking up here, we're approaching 0 from the right and observing our function value. So we're getting closer and closer and closer to 0 from the right, and it looks like our function is shooting off to infinity. So indeed, this limit is equal to infinity. What if we went from the other side? The limit as x approaches 0 from the left of 1 over x. Well, we are on this side now. We're getting closer to 0 from the left, and our function values are getting collapsed into a black hole. They are shooting down to negative infinity. That is something that we also have to know. And also, I could say that therefore, the limit as x approaches 0, all right, notice that I am taking, in this case, I don't care which side of 0 I'm looking at. In this case, I am purely on the left side of 0. In this case, I am purely on the right side of 0. But in this case, I don't care what side of 0 I'm on. But in this case, this is a big old problem. this number is the furthest away it can possibly be from this number, and I'm saying number, which is a little bit of a misnomer. This entity is very far away from this entity. It's certainly the case that these are not equal. So in this case, we would say that this limit does not exist. Oh, don't write equals. Does not exist. Why? Because in order to exist, hear this very, very loudly, in order for this to exist, the left-handed limit would have to agree with the right-handed limit. They do not in this case. And therefore, this does not exist. And this limit is actually the heart of the reason why you cannot divide by 0. Notice we were shooting x to 0, and that would be 1 divided by 0. And this limit is the big reason, or this is an explanation for why we can not divide by 0. Dividing by 0 is not a real number. 1 divided by 0 or anything divided by 0 is not a real number. It doesn't even exist. At least it doesn't exist in the real numbers. Okay. Anything else do I need? I got x approaches 0. And of course, you can say this should also be obvious, so I'm just going to write it down. The limit as x approaches negative infinity. See if you guys know. Hopefully you're playing along at home. That is also 0. If we are running to the left. It's approaching 0, but from the bottom side of 0. This guy approaches 0 from the top side of 0, whatever the heck that means. But anyways, this is a limit that we have to know for sure. We will use that in this week's practice video. So recognize that if I force the denominator to get arbitrarily large, then the limit is going to be 0. Related limits that we have to know. I hate being this mathematician that just states things without proving them, but I'm going to be that mathematician. Other really important limits. The limit as x approaches infinity of 1 over x to the n is equal to 0 for any natural number n. The limit as x approaches infinity of a to the power, of 1 over a to the power of x is equal to 0 as long as a is a real number bigger than 1. That's really important. And last one. So imagine you are collecting these as we go. The limit as x approaches infinity of, oh, maybe this isn't the last one. Shoot! Darn it. 1 over a to the x, or here. I'll do b. b to the x is equal to, oh, shoot, what is this equal to? Hold on, let me think. Infinity. If b is wedged between 0 and 1. Okay. I guess one more. The limit as x approaches infinity of the square root of x is equal to infinity, and therefore the limit as x approaches infinity of 1 over the square root of x is equal to 0. And actually, in a second, we're going to be able to prove this. So I don't know why I'm mentioning it, but here you go. I just kind of spurted off some really important facts that we will need to use in the future. And part 2 of this video. I created a PDF for you guys called The Limit Laws. Really, really important. Go to Canvas. There's a module either named Important Results or Results of Calculus or something like this. And somewhere in there, you will see a PDF called Results of Calculus. Open that up. Keep that with you right next to you while you are watching this video, because the rest of this video will be using this and referring to this throughout the rest of the video. Okay, so this is the set of limit laws. These are all really important, and I guarantee you guys, you are going to love these limit laws because they make our job so much easier. Once we have these guys proven, then we will be able to skip a lot of steps. We have been very annoyed with this epsilon delta sort of definition of a limit. I've put it here for convenience because it's so exhausting. And proving these limits exist and equal to some value is they straight up take 20 minutes to half an hour each time. So I'm telling you right now that once we have this set of these laws here proven, then our job is streamlined. So let me kind of read a few of these. Let me grab a highlighter. I guess pink is okay. So suppose L, M, A, and B are real numbers, that the limit of f of x as x approaches a is equal to L, so we know this limit exists, and that's really important, and that the limit of g of x as x approaches a is M, then all of these are handed to us as long as we are able to prove them, okay? This week's bonus video, I will dive in and prove the first 6 of these. I encourage you guys to try proving 1, 2, and 3. Those are not too bad. Well, I encourage you guys to try all of them. This is a little bit trickier. And then this one's pretty tricky. And same with this one. These guys are quite difficult. I'm not going to have time in class to prove these last 2. This is almost a direct result of this one. And this one's pretty tricky. We will be able to prove it in hindsight when we get to a little bit more theory in calculus. Once we talk about this weird thing called a derivative, we'll be able to retroactively sort of prove this one. So stay tuned for this week's bonus video for the proofs of all of these. But I just kind of want to talk about what these are saying as of right for right now. This says that the limit as x approaches a of any number. Let me zoom in. Sorry, it's a little bit blurry. This says that the limit as x approaches a of any number is equal to that number itself. So, for example, the limit as x approaches, who cares, 40, I don't know, of 9 is equal to 9. Okay, that's not surprising. 9 is not going to change no matter what x does. So how is 9 going to behave as x, runs to the beach? It's going to stay 9. That's what this first guy is saying. This next guy right here is saying the limit as x approaches a of x is, well, a. After all, what is x approaching? It's approaching a. So the limit of x as x approaches a is indeed equal to a. And again, that should not be surprising, and it's not hard to prove at all. In fact, a big hint, you let epsilon be bigger than 0, and guess what? The delta that will work will be epsilon. And you can think of it like this. This is a very simple line that goes through the Cartesian plane. It is a line of slope 1, so it looks something like this. It is a line of slope 1, and let's say, just for fun, that this point right here is A. And here are our epsilon values. All I have to do is create a perfect box. This value right here would also be A, except on the y-axis, because this guy has a slope of 1. So this distance right here is epsilon. This distance right here is epsilon. And we make a perfect square, so the delta in response to any epsilon is going to be epsilon. Anyway, so that's kind of just a rundown of the proof for that one. I really got to go. There's a lot I still have to talk about. Okay, this one says that if I multiply a function by a number, then what I can effectively do is take that number outside of the limit and worry about it later. Okay, so that's really important. What this one says is if I have something like this, the limit as, I don't know, t approaches 2 of 7 times h of x, that is the same thing as 7 times the limit as t approaches, as t approaches 2 of h of t is what I meant. This should be a t. So that's what this is saying. Also, just since we're here, I would say this, since I just made that mistake. The limit as, here, let me do it somewhere else, maybe up here. The limit as x approaches 4 of f of y. Notice this, f is a function in terms of y, but the limit is as x is approaching 4. So it's actually kind of like an extension of this first limit law, that this limit, f of y, is not going to change at all as x changes, because this is a function in terms of y. So it's understood that this is actually simply going to be f of y. Oops. F of y. So make sure that the variable that's moving is also the independent variable of the function in question. So that's kind of like a tangent fact that we need to know. That is really important. And maybe one more thing I could say, the limit as x approaches t of x to the third plus t to the third, or to the second, that is going to be equal to, so the thing that's moving is x. So this x is going to approach t, giving me t cubed plus t squared. Whereas if I had the limit as t approaches x of x cubed plus t squared, the thing that's moving is the t. So this x cubed, treat it like a constant, like a number. But t is approaching that number x, and this would be the thing that's moving is t, so this guy is going to approach x, and that's going to give me x cubed plus x squared. Okay, so make sure you understand what's moving in your limit and things like that. Okay, anyways, on to the big limit laws. It is true that if the limit as x approaches a of f of x is equal to L, and if the limit of g of x as x approaches a is m, then the limit as x approaches a of f of x plus g of x is equal to simply L plus m. I would read this limit law as, this is limit law 4, the limit of a sum is the sum of limits. Notice that what I could do is another name for L. So what I'm going to do is replace L right here. Another name for L is the limit as x approaches a of f of x. And another name for m is the limit of g of x as x approaches a. So notice what kind of happened. So again, all I did was I replaced L with what it literally is, and I replaced M with what it literally is. It looks like this limit kind of distributed over this sum, and that is what this limit law is saying. The limit of a sum is the sum of limits. That's how I would say that. We call it limit law 4 for shorthand. And because of that, another way you can write or read this one is the limit of a product is the product of limits. And so what that means is we can literally distribute this limit across a product. Notice that that is kind of new to the mathematical world. You don't usually distribute over multiplication. You can distribute over addition. That's the distributive property. But distributing over multiplication is a little bit, I don't know, it's a little bit weird, kind of something new. And of course, you can replace L with its literal name if you want to see this law in a different way, and replace M with its identity, the limit as x approaches a of g of x. But this says the limit of a product is the product of limits. And of course, we have the limit of a quotient is the quotient of limits. All right, all of these are very, very, very important, and these are going to streamline the process quite greatly. And as sort of an example to show you guys, this was the limit that we worked on in the first practice video. So the last week's green bordered video, and I'm going to show you that with these laws, we can crush this in a matter of minutes or perhaps less. Here's what I'm going to say first. I think I know. Okay, so like I said, we have not proven these. In the bonus video, we will prove these. I'm going to be a bad mathematician. We're all going to be bad mathematicians, and we are going to proceed as if we have proven them. Let's assume that we know that all of these are true. Again, that's bad math. You don't ever assume things are true unless it's actually been proven, and you have proven it preferably. But we will prove it a little bit later. So let's assume they're true, kind of observe how they behave, and then in this week's bonus video, we will prove them. Okay. So, using these limit laws, I have the piece of paper right here handy. I think I know, as I was saying, this limit can distribute to all of these pieces. All right, watch this carefully. And I'm going to justify every single one of my steps. I think using one of my limit laws, and again, you guys should have the limit laws in front of you. I can rewrite this limit like this. Okay, so what limit law did I just use? All I used was the limit of a sum. So I have the sum of three objects right here is the sum of limits. All right, which one says that? That is limit law 4. So all right, because LL4. That justified that first step. Oh, but I see something else I can do. Another name for this first limit. Or how about this? The first thing I'll do is this. I can use the first limit law, LL1, to say the limit of 4 as x approaches who cares is going to be 4. 4 is a constant. It's aptly named a constant. In other words, it is not affected by change. This limit is literally the tool that we use to study change, but if something's not changing, this limit has no point. We can get rid of it. That is the first limit law. So I'm going to replace that. So this is the same thing as the limit. I'm just going to copy down everything else. 3x squared plus the limit as x approaches 2 of negative 5x. And as I said, this is simply 4, and that is because of LL1. Okay, but I'm thinking that the third limit law is really helpful. Indeed, I think this 3 can be taken outside of the limit, and this negative 5 can also be taken outside of the limit. So let's use the third limit law twice. This is the same thing as 3 times the limit as x approaches 2 of x squared plus, or how about this? Minus 5 times the limit as x approaches 2 of x plus 4. And again, I just used the third limit law, and I really hope you guys have this right in front of you. All of these limit laws right in front of you as I'm doing these. So this is LL3, and I technically used it twice. All right, so check this out. This object right here, that I can use the second limit law. So the limit of x as x approaches 2, well, duh, x is going to 2. So the limit is patently obvious. Still have to prove it, though, and we will. This is the same thing as 3 times, and I'll spend a little time explaining this one, as x approaches, the limit of x squared as x approaches 2, minus 5 times 2 plus 4, okay? So that was because of the second limit law, LL2. And this guy. Okay, so what I could use is LL7, but kind of to motivate how to prove LL7, I'm going to say that this is the same thing as 3 times the limit as x approaches 2 of x times x, all right? Minus, here, I hope you guys don't mind. I'm going to do some quick arithmetic. That's minus 10 plus 4, that's minus 6. Why did I write x squared as x plus x? Because now I can show you that the limit of a product, is the product of limits so it's kind of like I distributed this limit to both x's. And guess what? Okay, so let me make sure, I guess the because here is not so much a limit law, but x to the nth power is by definition x times x times x times dot 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 x n times. That's a definition. It's not even a theorem. But this was a limit law. This is because of LL5. In other words, the limit of a product is the product of limits. And guess what? I'm going to use LL2 twice to say that this is 3 times 2 times 2 minus 6. This is LL5 2 times, giving me a final answer of 6. All right, and I hope that is what we got when we did this limit in the bonus video. But just to see how powerful that was, if we know that all these limit laws are true, then they are huge, huge tools. Okay, okay, that was great. The big thing I want us to focus on right now, first of all, again, I'm going to prove all these in the bonus video. I'm running out of time. I got 20 minutes. I want to finish in 20 minutes. I don't think it's going to happen. It's going to be a long theory video, guys. Thanks for hanging out. Double-sided, if and only if, equal one-sided, equal to the one-sided. So the limit of f of x as x approaches a is equal to L. I just wanted to mention this real quick until we get to the really big, nice theorem that we have right here that we're going to spend the rest of the video on. If and only if, remember, biconditional. That's what that means. The limit of f of x as x approaches a from the left is equal to L, and that's also equal to the limit of f of x as x approaches a from the right. Really, really important. Okay, so that's something we should prove, and I mentioned it earlier. And we're about to use this, and we have to assume this is true for the next big theorem. Really nice theorem. Famous theorem in calculus. This is kind of like one of the first big momentous points in calculus, and that's when you introduce the squeeze theorem, a very, very big limit theorem. And what it says is if f of x is a function that's always below or equal to g of x, and h of x is a function that's always above or equal to g of x, in other words, g of x is squeezed between f of x and h of x when x is near some number a, except possibly at a. So again, that's a reoccurring theme in calculus. You don't care about the function values at the limiting value, because often you never can reach that limiting value. If g of x is sandwiched between f of x and h of x when x is close to a, this is indeed sometimes called the sandwich theorem. And we happen to know that the limit of f of x is equal to L. In other words, this f is approaching L when x gets close to a. And also the limit of h of x is equal to L. In other words, h of x is getting close to L as x gets close to a. But g of x is always crushed between these two guys. So if f of x is getting close to L and h of x is getting close to L, then g of x has nowhere to go. In other words, the limit of g of x as x approaches a also must be equal to L. This is called the squeeze theorem, and we're about to prove it. Let's do it. I also made a nice picture over here. All right, so this is the squeeze theorem. You can kind of see it in the picture. We have an f of x right here. It's forced below g of x. G of x is in between h of x and f of x when we are close to a. And if you observe, the limit of f of x as x gets close to a is indeed equal to L. And h of x, the limit of h of x as x gets close to a, is also equal to L. And since g of x is necessarily sandwiched between them when x is near a, then g of x has nowhere to go, and indeed, as the picture kind of shows, the limit of g of x as x approaches a also must be L. So I have it all right here. Let's prove this rigorously. Let me hop into it. I'll use this guy. Nope, that already has a... What color? I guess just gray. Proof. Let epsilon be bigger than 0. Okay, so this is huge. Since the limit as x approaches a of f of x is equal to L, so that is something we're assumed to be given. We have for free in our proof that this is true and that this is true. All right, so technically, I should say at the beginning of my proof that let's suppose that f of x is less than or equal to g of x, which is less than or equal to h of x when x is near a, except possibly at a, and let's suppose that this is true as well. So we are assuming that this is true, and we are assuming that this is true, and our goal in the proof is to show that if both of these are true, then this no doubt must be true as well. So one of the things I have assumed to be true, or that I have for free, is that the limit as x approaches a of f of x is equal to L. That's what I'm saying. Since the limit of f of x as x approaches a is equal to L, what that means is, by definition, we know there exists some delta, I'll call it delta f, bigger than 0, such that f of x minus L is less than epsilon whenever 0 is less than x minus a, which is less than delta f. Okay, so notice that this is kind of like new to us. Usually it's our goal to find delta f to show that this is true. But since we know that this is true, it's given that the limit of f of x as x approaches a is equal to L. What that means is that no matter what epsilon we are handed, we will always be able to find the delta, okay? So notice that the slight difference in what we're doing. We're not proving this is true. We know this is true, which means that any challenger can be met with a response. Whereas prior to this video, we were trying to show things like this were true. In other words, we had to show that given any challenger, we can always find a response. But it's almost like somebody already did all that work for us and said, yeah, we can always find a response given any challenger. So we know this delta exists. That's what I'm trying to say. But if that is true, that means that negative epsilon is less than f of x minus L, which is less than epsilon whenever this is true. So these dots mean, these means I'm taking this down as well. Okay, and again, that is a synonymous phrasing for this sentence right here. This sentence says the same thing as this. But that implies subtracting L everywhere, that L minus epsilon is less than f of x, which is less than epsilon plus L. So I added L to all sides, all right? But this is only true, of course, this is only true whenever 0 is less than the distance between x and a, which is less than this delta f, okay? So I'll write whenever, yada, yada, yada. Oh, but something here is going to be really important, so I'm going to kind of box it. I'll box it in yellow. I know that this inequality is accomplished as long as this is accomplished. Okay, oh shoot, but I also know the limit of h of x as x approaches a is equal to L. So I'll write that in my proof. Also, oops, don't want to use that. Also, since the limit as x approaches a of h of x is equal to L, and remember, we have, at the beginning of our proof, we've accepted a random epsilon. And we are indeed on the hunt for a delta, but a delta, we want that delta to be associated for g of x. We know a delta exists for f of x. We grabbed it already. We are about to grab a delta that exists for h of x, and we're going to do something with those deltas to show that a delta exists for g of x. All right. Since the limit of h of x as x approaches a is equal to L, we know there is some delta sub h bigger than 0 such that, and this next part is going to be very familiar, h of x minus L is less than epsilon whenever 0 is less than x minus a is less than this delta h. Okay, so this is the associated delta for this function h. Okay, we know this delta exists because it's given at the very beginning that this is true. But this says the same thing. I'm going to skip a few steps. I'll tell you verbally, follow this same process, but for h of x, that implies that L minus epsilon is less than h of x, which is less than epsilon plus L, whenever 0 is less than x minus a is less than delta sub h. Okay, there's an inequality right here. I would really like to have this inequality. And you might get the idea because we haven't used a piece of information yet. We've used already, so far we've used the fact that the limit of f of x is equal to L and the limit of h of x is equal to L. We haven't used this inequality yet. In other words, we know that L minus epsilon is less than f of x. Oh, but f of x is definitely less than g of x. We also know that g of x is less than h of x. Oh, shoot. But h of x is less than epsilon plus L as long as we force x to be close enough. We need this to be accomplished and this to be accomplished in order to be awarded these two yellow tokens. So how do I force both of these to be accomplished simultaneously? It's the same story, you guys. So choose a delta sub g bigger than 0 such that delta sub g is less than delta sub f and delta sub g is less than delta sub h. In other words, this will be accomplished whenever the distance between x and a is less than delta sub g because of this condition right here. Also, this will be accomplished whenever the distance between x and a is less than delta sub a, or excuse me, the distance between x and a is less than delta sub g because of this condition right here. All right. So I'll say, I wonder the best way to say this. Then, if 0 is less than, this will be good. X minus a is less than delta sub g, then 0 is less than the distance between x and a is less than delta sub f. Okay, and that's because of this. And of course, that implies L minus epsilon is less than f of x. Also, if 0 is less than x minus a is less than delta sub g, then 0 is less than x minus a, which is less than delta sub h, and that's because of this condition. It's out of frame. So that h of x is less than epsilon plus L. And then I'll say, hence, L minus epsilon is less than f of x, which is less than or equal to g of x, which is less than or equal to h of x. And again, this part right here is given to us. That's free. We know that's true for all x near a. All right, we're very close to a. And h of x is less than epsilon plus L. And that says the same thing as L minus epsilon is less than g of x, which is less than epsilon plus L. Subtract L from all sides of this inequality, and notice that that says precisely the same thing as the distance between g of x and L is less than epsilon as long as 0 is less than x minus a is less than delta sub g, and that says that therefore the limit as x approaches a of g of x must be equal to L, and we have just proven the squeeze theorem. Very nice. Okay, so that's hopefully intuitively true, and the proof, I like it. That's a kind of the first style of proof that we have, where it's given that the limits exist, and you have to grab deltas that you know exist because you know the limit exists. And we're no longer hunting for deltas. We are handed the deltas, kind of, so to speak, in this case. Okay, I want to use this a few times, and I want to use it with some trigonometry. So let's say I got a unit circle right here. We have to collect some famous limits using this squeeze theorem, so to speak. I have the unit circle right here. In other words, this is a circle of radius 1. And let's say I go some angle theta in the positive direction. And I want to talk about, let's see, what do I want to talk about? I don't know. What is this distance? Let's see if you guys know your trigonometry. I think that this distance right here, if I were to go from this random point straight down so that this makes a right angle, that distance by definition is sine of theta. All right. Now, this distance right here, hopefully you remember, that distance is cosine of theta. Okay, very nice. And I don't know, that makes this distance right here 1 minus the cosine of theta. Convince yourself that that is true. Big hint that this distance is 1, okay? It's on the unit circle. And I want to talk about a few other things. One more thing, actually. I like this proof. This is exciting. This distance right here. Nope, let me try again. Here's something I know about that orange distance. I think it is guaranteed to be less than this pink distance. I don't want to use pink. Yellow distance right here. All right. Now, I think there is a way that we can find yellow distance and orange distance, okay? Let me name these maybe. So C. Nope. No, I don't want to call that C. I'll call that D, or A for arc. arc length. And then let's call this orange distance C, okay? Hopefully you guys are well adept and you know how to find C. I'm going to talk about how to find A real quick. I'm going to do a quick sketch. Notice that A is to the entire... Oh, shoot, I can't use C. Bad. L, of course. A is to the entire way around the circle. The proportion of this distance right here to the distance all the way around the circle has to be equal to this arc or this rotation to a rotation all the way around the circle. All right, so let me say that again. This arc is the same proportion, this arc to the arc all the way around the circle is the same proportion as this arc to the, or this rotation to the rotation all the way around the circle. In other words, A is to the circumference as theta is to the entire rotation around. That's 360 degrees or 2 pi. Okay? But what is the circumference of a circle of radius 1? That is simply 2 pi. So A divided by 2 pi is equal to theta divided by 2 pi. 2 pi's cancel, telling me that this arc length is theta units long, okay? So that arc length is theta, all right? So A equals theta. That's really important. Now, another observation clearly is that A is bigger than or longer than L, all right? L is the shortest distance between these 2 points. L is the shortest distance between these 2 points. And A contains, or this arc contains points that are not on L, which means that this arc must be bigger than L. And how the heck do we find L? Oh, that's of course the Pythagorean theorem. So I think L squared is equal to something squared plus something else squared. And that's going to be 1 minus. Notice the triangle I'm looking at right here. This triangle right here. It's a right triangle. And so I can use the Pythagorean theorem. So this, what we have here is 1 minus cosine theta squared. And we also have sine squared. This is the Pythagorean theorem. No surprises. But I wanted to make an observation. Oh, yeah. Okay, so also this says that, right here, this says that L squared, oops, wrong color. L squared is clearly less than A squared. That's really important. So that's something I'm going to have to use. But notice this. This is a positive value. Okay? And this is also a positive value. So this object is certainly bigger than, watch this. That is bigger than, and I'm going to have to drop colors, sine of theta squared. Okay, so here's what I want to do. Watch this. My inequalities are kind of everywhere. Sine of theta squared is less than L squared, and L squared is less than A squared, okay? Or theta squared. So what that means is sine of theta squared is less than A squared. Let me write that down. And A, of course, is equal to theta. Okay. What that means, taking square roots, oh, by the way, also both of them are positive. Notice sine is a positive distance here. Sine in the first 2 quadrants is positive. And theta is also positive, as it is a distance. So if I take square roots, what is the inequality that I get? I need us to remember that star squared under the square root is by definition, well, actually it's not by definition, we prove it, that is equal to the absolute value of star, okay? So the absolute value is about to show up. Let's see what we just said. What we have here is that the sine of theta in absolute values is less than the absolute values of theta. But I think there's another way to say that. Negative theta is less than sine of theta, which is less than theta. Okay? So that's the definition or a restatement of this guy right here. Oh, shoot. But what that means is I can use the squeeze theorem. Notice that the limit as theta approaches 0 of absolute value of theta, so I'm taking the limit of this side as theta approaches 0, that is definitely equal to 0. Also, the limit as theta approaches 0 of negative absolute value of theta, that's definitely going to be equal to 0. In other words, if I took the limit of this guy as theta approaches 0, is equal to 0, which forces me to conclude that the limit as theta approaches 0 of sine of theta is equal to 0. All right, so this is something that we need to know for sure. You might be thinking to yourself, why can't we just plug in 0 for theta? Why can't we just grab theta and plug it in right here? Because you're assuming something about sine that we don't know yet. You don't know that sine behaves in that way. You don't know that you can just pass the limit through this sine function. Turns out you can, but we have to first say something about sine, in particular that it is a continuous function. We don't even know what that means yet. So we just proved that this is true without the idea of continuity. Okay. Now, turns out, or I want us to observe that over here, there is no particular reason why I did this one. Indeed, I could also say from the beginning, also, L squared is bigger than this thing, but this thing is certainly bigger than or equal to, ooh, I missed that. It should be equal to or equal to. Bigger than or equal to 1 minus cosine of theta, all squared. And you guys, I'm going to have to force you guys to do this. Follow this same logic to conclude and the fact that L squared is less than A squared, to conclude that the limit as theta approaches 0 of cosine of theta is equal to 1. We need to take that one with us. And now we are going to go to a very similar proof, but this is a famous result, okay? We want to figure out what the limit as theta approaches 0 of sine of theta divided by theta is. And this is the last thing we're going to do. It's going to be a long theory video, but it's a really important theory video. Notice this. I cannot simply pass the limit through. In my numerator, I will have 0. In my denominator, I would also have 0. We just proved that if I just pass the limit through the numerator, the limit as theta approaches 0 of sine of theta is equal to 0. And the denominator is certainly going to 0, so we can't pass the limit through, but we still want to observe what this limit is. So we call that an indeterminate form, 0 divided by 0. Not good. Other ones are infinity minus infinity. That's called indeterminate form. 1 to the power of infinity, 0 to the power of infinity, Infinity to the power of infinity. Oh, I actually think that one's just infinity, so that's all good. What other ones are a problem? Oh, infinity divided by infinity. That's also an indeterminate form. So, in other words, if your limit ever poses these sorts of shapes, then you have more work to do. It's indeterminate. You can't determine anything. This is one of them. This one in particular. So let me also add 0 divided by 0. This one is 0 divided by 0. So we want to figure out what this limit is. It might not exist. It might exist. That's what all these mean. Indeterminate. You don't know if it exists or not, or what it equals to. This is this one. We need a little bit more work. We have to do a little bit more work. All right, let's see this proof. This is one of my favorites, because it involves geometry, and we all love geometry. I'm going to observe 3 shapes and discuss their areas. So the first one I'm going to do is this. This is also a unit circle, by the way. Which means that this distance from here to here is just 1. All right. And I do want to talk about, again, this distance right here. That distance is, yet again, just sine of theta. Okay? But not just that distance. I want to talk about what the area of this shape is. Okay, so zone in. Talking to myself. Zone in. Make sure you write these lines well. So hopefully all of us are thinking to ourselves, oh, that's a triangle. That's not bad. I agree. So the area of the blue shape, we want to figure that out. I think that is equal to 1/2 base times height, right? So here's the base all the way across here. That's 1, a distance of 1. Oops, forgot the parentheses. This is a distance of 1, a height of sine theta. So we just have 1/2 base times height. And the base is 1, and the height is sine theta, so 1/2 sine theta. Okay, that's huge. But I want to talk about another shape, a new area, and that's going to be this guy. I'll do orange. What if I wanted to talk about the circular sector? Zone in, and that's outlined like this. And just like we did a sort of proportion argument for the arc length in the prior kind of exercise, we're going to do a proportion argument for the area of that orange sector right now. I think I know that the area of that orange sector is to the area of the circle, which is pi, just as theta is to an entire rotation. So that's just theta over 2 pi. Okay? Pi's cancel, telling me that the area of that orange sector is theta halves. Okay, let me add that. The area of the orange sector is theta divided by 2. Okay, that's really important. And the last one, the last shape I want to look at is this one. I'll go pink, green. Talk about a new triangle. Imagine that's going straight up. It kind of looks like it's going straight up. Okay. Last triangle I want to look at. We want to figure out the height of this triangle. Let's just call it y. Well, here's what I know. I also want to talk about the area of the triangle. To solve for y, I think I know that the tangent of theta, so that's tangent of this angle down here, that's going to be y divided by 1. Oh, look, that gives us a formula for y. In other words, y is simply the tangent of theta. And if I know the height, then I know the area of that triangle. So that the area of that green triangle is equal to 1/2 base times height, 1/2 base, 1 times height, tangent of theta, telling me the area of the green triangle is 1/2 tangent of theta. Okay, now, here's my argument. Look, the blue area. That is certainly less than the orange area. And that is certainly less than the green area. Right? Based on the picture. So what that means, this is where I'll drop color, I think that says that 1/2 sine of theta is less than theta over 2, which is less than tangent of theta over 2. Okay? Multiplying everything by 2 and recalling that sine of theta in this case is bigger than 0. And then let's divide everything by sine of theta, which is bigger than 0, so I don't have to change any directions. Hopefully we remember that tangent of theta is simply sine over cosine. So if I divide it by sine, that's just going to be 1 over cosine, in other words, secant. And then I reciprocate everything. That tells me that 1 is bigger than sine of theta over theta, which is bigger than cosine of theta. Oh, look, this looks like perfect squeeze theorem territory. Indeed, notice that the limit as theta approaches 0 of 1 is equal to 1. That's the first limit law. This guy, as theta approaches 0, that's equal to 1. Oh, sorry. Theta approaches 0 from the right. All right? Because theta is positive. Our theta measure was positive. It's a positive theta measure. That's important. And that's how I know that sine of theta is also positive. And I know we just proved that the limit as theta approaches 0 from the right, well, we proved it for a general from the left or right of cosine of theta is equal to 1. So this approaches 1 as theta approaches 0. Duh. This also approaches 1 as theta approaches 0. So what must this approach, since it's wedged between these guys? What I'm going to say is, therefore, by the squeeze theorem, I can spell, the limit as theta approaches 0 from the right of sine of theta over theta is equal to 1. But I think we're about to make an argument that it also approaches 1 from the left, so let's do that. So notice or recall that sine is an odd function. In other words, what that simply means is that the sine of negative theta is simply equal to negative sine of theta. And therefore, the sine of negative theta divided by negative theta is equal to negative sine of theta divided by negative theta, which is equal to sine of theta divided by theta. In other words, sine of theta over theta is even which it means it's reflected over the y-axis. It looks exactly the same. Or in other words, if you'd like, you can say something like this. That says, therefore, the limit as theta approaches 0 from the left of sine of theta divided by theta, that's going to be equal to the limit as theta approaches 0 from the right of sine of negative theta divided by negative theta. But this thing in the limit is the same thing as sine of theta over theta. Zero from the right of sine of theta over theta, which we just proved was equal to 1. So look at both sides. We just showed that the limit from the right is equal to 1, and we also know that the limit from the left is equal to 1. If both limits agree, then you can say conclusively that the limit as theta approaches 0 without any superscript of sine of theta divided by theta is equal to 1. This is a famous result, and we all have to know this by heart. It should be second nature to notice that the limit as theta approaches 0 of sine of theta divided by theta is equal to 1.